give you a flavor of what that means. If we were to walk outside and look up, right now we'd see clouds, but if it wasn't cloudy, you'd see stars. At the right time of the month, you'd see the moon. If you knew where to look, you could see planets moving slowly through the sky. But what if you had gamma-ray vision? If your eyes were sensitive to gamma rays and you looked up, you'd see nothing because the Earth's atmosphere absorbs gamma rays. But if you put yourself in orbit and you were able to view the sky in gamma rays directly, you would see a completely different world. Our Milky Way Galaxy, which in visible light is a faint, cloudy glow, in gamma rays is the brightest thing in the sky. More than 80% of the gamma rays that we see with Fermi are produced in a diffuse flux from our Milky Way. And they're produced when charged particles moving at close to the speed of light smash into gas and other radiation fields in our galaxy to produce gamma rays. But if you look at this map of galaxies, so this map, let me go back one, this map is in galactic coordinates. And what I mean by that is you're seeing the entire sky unrolled, and the plane of our galaxy is this stripe down the center. That's the very bright thing that you're seeing. But if you look at this map, you can also see that there's more than just the flux, the diffuse glow of gamma rays from our Milky Way. There are also individual sources of gamma rays. Now, if you're viewing the sky in gamma rays, we're not seeing planets that are just sitting there. We're not seeing stars unless they're exploding. What we do when we're viewing the sky in gamma rays is hone in on some of the most extreme places in astrophysics. Examples of those include pulsars. A pulsar is a rapidly spinning neutron star. A neutron star is made of the densest form of matter that we know before you get to a black hole. You take something that's about the mass of the sun, you squeeze it down so it fits in a radius of a couple of tens of kilometers. You give it a magnetic field that's 1,000,000 times more intense than any magnetic field we can generate here on Earth. And you spin it as quickly as a ceiling fan. And those are the kinds of conditions that can rip particles off the surface of the neutron star and accelerate them to extremely high energies that then produces pulses of gamma rays just go pulse, pulse, pulse. We also see objects known as active galactic nuclei. These are systems very far from us that contain a supermassive black hole at their center. These black holes contain 1 billion times the mass of our sun. Material is swept in to the supermassive black holes, and in the process, some of them produce jets of particles that are moving close to the speed of light. And for some of those objects, the jets are pointing right at us. And those objects we see in gamma rays. And when we see them in gamma rays, they very often change in intensity by factors of tens to hundreds on timescales of hours and days and years. The gamma ray sky is constantly changing. We also see gamma ray bursts. A gamma ray burst is a very short, brief, intense flash of gamma rays. It's produced when a massive star reaches the end of its life and explodes, collapsing into a black hole. Sometimes a gamma ray burst is produced when two neutron stars merge together, also collapsing into a black hole, and in the process releasing a huge amount of energy. So this gives you a flavor of the kinds of things that we're studying when we're looking at the gamma ray sky. And then finally, one of the exciting things about our field is that there's a lot of things that we don't know. There are many gamma ray sources in the sky that we don't know what their origin is. We've been doing optical astronomy for thousands of years, but viewing the sky in gamma rays is new, and is something that we've only been able to do for the last few tens of years. So we're really opening our eyes in an entirely new way for the first time. So to get a little bit more precise about what we're doing, this is an electromagnetic spectrum. An electromagnetic spectrum, which you're probably all familiar with, is how we describe the wavelength or frequency or energy of light. And you start over on the low energy, long wavelength side with radio. And as you get more and more energetic, you go from radio to microwave, from microwave to infrared, to visible, which is what we see with our eyes, that tiny little slice in the middle, ultraviolet, X-ray, and then finally gamma-ray. Underneath this electromagnetic spectrum that I've sketched here, I'm also showing the energy range that are covered by the two instruments on Fermi, the GBM, the Gamma-Ray Burst Monitor, and the Large Area Telescope, the LAT. And what I'd like to point out is that those instruments alone are the equivalent of being able to view all the way from microwave through to X-ray in a single instrument. So we call things gamma rays, but that's only because we don't have any more words to describe energies above a few hundred keV. When we see a gamma ray, we know we're seeing charged particles that have had at least that energy or more. And we know this because it's impossible to heat something up hot enough that it radiates in gamma rays. Gamma rays are always produced in what's known as non-thermal processes, places where particles are accelerated to extremely high energies. So if we want to understand the highest energy things in the universe, where cosmic rays are produced, the highest energy particles that we know of, wherever that's happening is almost certainly going to produce gamma rays as well. This is a picture of the observatory taken a few weeks before launch when the satellite was sitting in the rocket fairing. The box on the top is the Large Area Telescope. So it's not really a telescope, it's a detector. It operates from 20 MeV to over 300 GeV. So to put that into different terms, 20 MeV is about 20 million times more energetic than an optical photon. 300 GeV is 300 billion times more energetic than an optical photon. So we're dealing with extremely high energies for each individual gamma ray that we're seeing. The second instrument, the Gamma-Ray Burst Monitor, operates from the X-ray, which at 8 kiloelectron volts, that's 8,000 times the energy of an optical photon, to 40 MeV. And what the GBM does is detect brief flashes of gamma rays, and later I'll show you some examples of the kinds of things that we see. So how do we detect these gamma rays? To understand how we detect the gamma rays, you need to understand how the gamma rays interact with matter. At the energies that we're talking about in the Large Area Telescope, each gamma ray has an enormous amount of energy. And when it interacts by converting to an electron and the anti-particle to the electron and positron. In other words, the energy of the gamma ray is converted into matter. And that's what Einstein's equation E equals mc squared is telling us, that energy and mass are equivalent and that you can convert energy, a gamma ray, into mass, the electron and positron, but only if you have a lot of energy. So the way that this works, so this is a toy picture of our detector. The gamma ray comes in at the top. It interacts in a layer of tungsten to produce an electron-positron pair. The electron and positron then move through the detector, and we can measure the track of the electron and positron so we can figure out where the gamma ray came from. And then we measure the energy that's deposited in what's known as a calorimeter at the bottom. The components of our instrument, we have a tracker that has almost 1 million channels of electronics. The total amount of silicon in this would make millions of digital cameras. We've got a calorimeter that is an array of scintillators. A scintillator is a material that can convert energy into optical light, so we can measure how much energy has been deposited in it. And it's surrounded by what's known as what we call an anti-coincidence detector, and that allows us to distinguish between charged particles and gamma rays. This instrument reads out almost 1 million pieces of information, several thousand times per second, using an amount of energy that is about the same as a hairdryer. And one of the challenges in building an instrument to operate in space is thinking very, very carefully about how to use as little power as possible. And this isn't because we can't generate the power, it's because we can't dissipate it. This is an animation that shows in a more active way what's happening. So the gamma ray comes in, it interacts, turning into an electron and positron pair. The charged particles are then tracked in the detector. They wobble a little bit from multiple Coulomb scattering, but on average we can reconstruct them back to give us a picture of where the gamma ray came from. We have over 5,000 individual sources of gamma rays in the sky. And that's exciting to us because before we launched Fermi, there were only a few hundred gamma ray sources known. But what's really exciting is that because our instrument has the ability to go to even higher energies, I've just shown you, this map shows you a map of the sky above 1 GeV, 1 giga-electron volt. But I can also go 50 times higher in energy and show you a different map. And this has fewer sources, but some of these objects are not the same as the ones that we're seeing at lower energies. We see new things when we can see the sky at different energies. And in particular, you might be able to see a faint haze above and below the center. And those are one of the dramatically new things that we found with Fermi that I'll describe a little bit later. The field of view of the LAT is about 20% of the sky. And when we make observations, we sweep the field of view across the sky in a way that every 3 hours we see the entire sky. And this gives us an ability to see how the gamma ray sky is changing with time. And this is important because we know that that gamma ray objects are changing rapidly. Things are exploding. We're seeing the changes of accretion on the supermassive black hole that's giving us these changes in flux. So what you're seeing here is how the if you imagine taking the field of view and just move it across that map, what we see every 3 hours, how this motion happens. And what this means is that I can show you a map of the sky in time. In this movie, every frame is 1 day, and you're looking at the first year of observations with Fermi. And we've made this map by taking the North Galactic Hemisphere, which is on the left, and the South Galactic Hemisphere, which is on the right. So the very bright galactic plane is on the edges. So what you're seeing are the active galaxies, these supermassive black holes, changing drastically in flux. Can anyone see anything else? Can you see something moving? So there's, if you look there, you'll see the sun moving through the sky. And this brings me to one of my other points. The gamma ray sky is very unusual because the sun is not particularly bright. You couldn't take an optical picture of the sky with the sun up, but it's not a problem in gamma rays because the sun is not normally a particularly bright object. And in fact, what you're seeing here in the sun isn't the sun directly shining. The reason that we're seeing those gamma rays is that these cosmic rays, the very energetic charged particles, are smashing into the solar surface and producing the gamma rays that we see. And if I'd made this map on a different timescale, you would actually see the moon as well. The moon in high-energy gamma rays is brighter than the sun. And that's because the moon doesn't have a magnetic field, so all of the charged particles can arrive at the surface. For the sun, the magnetic field bends some of them away. The second instrument is the gamma-ray burst monitor. And the gamma-ray burst monitor is a set of scintillators, of 14 scintillators, 7 on one side of the satellite and 7 on the other. And with these, they view the entire sky. So everything that is away from the Earth, you're seeing things in the universe. But the detectors also see the Earth, and with those, we see flashes of gamma rays from the Earth's surface itself. And these gamma rays we see intense bursts of gamma rays from enormously different events. So we see bursts of gamma rays from gamma ray bursts. These are signaling the births of black holes very, very distant from us. We also see outbursts of gamma rays from objects known as magnetars. These are highly magnetized neutron stars that have a disruption in their crust and release very large amounts of energy in short bursts. These are in our galaxy, so closer. We see flashes of gamma rays from our sun when the sun is active. Right now, the sun is in a quiet phase, so it's actually been several weeks since we've seen a solar flare. But a few years ago, we were getting many solar flares per week. And then finally, we see flashes of gamma rays from the Earth. We see very short millisecond bursts of gamma rays that are produced by intense thunderstorms. And as I'll show you in a moment. So what I'd like to do with the rest of the talk, and I've realized I've absolutely no idea what the time is. Okay. So I'm just going to keep talking and assume I'm on. So I want to just talk about some of what I've done is gone through each year of the mission, and I've picked a few of the results that I think have been particularly exciting to give you a flavor of the range of things that we've done. So one of the very first things that we did is when you first launch, you want to make sure that your instrument is working. So what we did is, even though our normal mode is to survey the whole sky, we decided that we wanted to point in one place and make observations of a bright gamma-ray source. The bright gamma-ray source that we chose was an object that was known from the previous gamma-ray mission called Egret. And Egret told us that there was a bright source of gamma rays, but it couldn't tell us what those sources of gamma rays were. So if you look at the image on the left-hand side, what you're seeing there is a radio map of the supernova remnant CTA. And superimposed on that blue circle is the location error of the previously known gamma-ray source. So the problem is that you couldn't tell whether the gamma-ray source was associated with the supernova remnant, the blurry bit, or with the point source, which is located in an X, which was an individual point source of X-rays. With 2 weeks of Fermi observations, we were able to get the location down to that small red circle. So we now knew that the gamma-ray source and the X-ray source were almost certainly the same object. But what was particularly interesting is that when we looked closely at the data, we realized that if you bin the data in time bins of 316 milliseconds, that they form a pattern. So this object is rotating once every 316 milliseconds. And in each rotation, you're seeing one large pulse. So this object was a pulsar. We were able, in the gamma rays, to determine how rapidly it was rotating, and it had not been known as a pulsar before that. A pulsar, I mentioned this before, but a pulsar is a neutron star, very, very dense object, rapidly rotating. Now we've discovered that we can identify a pulsar in the gamma rays alone. There were no radio signal, and the X-rays were not seeing pulsations. The reason this was exciting is that we then continued to make observations, and we realized that the sky was peppered with these objects that were only detectable in the gamma rays. So these extraordinarily dense, extraordinary objects, a large fraction of them were only findable in the gamma rays, and we didn't know that they were there until we had observations with Fermi. And we used to have an idea that the way a pulsar worked is that you imagine you have a lighthouse, and that if I'm a lighthouse, and I'm going around, you're not going to see anything because the emission is beamed above your heads. And if you happen to be in the right place, you would see the pulses. Now you change your idea, and you imagine instead of being like a lighthouse with a beam, it's more like a fan. And now as I go around, everybody gets to see the pulsar. So what we think is happening is that in the gamma ray, the emission is like a fan and is radiated everywhere and is always findable. And in the radio, it's more like a lighthouse. So for young pulsars, you can more easily find them in the gamma rays than in the radio. And this has been one of our, this kind of object has been one of our success stories. I mentioned thunderstorms, terrestrial gamma ray flashes, so now we're coming right back home. A terrestrial gamma ray flash is a very brief flash of gamma rays with a characteristic spectrum, distribution of gamma ray energies. And we knew that these kinds of objects were coming from thunderstorms because if you plot the location of the spacecraft at the time that we're seeing these objects, that consistently fall on top of regions of the Earth that had large thunderstorms. But sometimes they don't. So in 2009, on the 14th of December 2009, we saw a really unusual terrestrial gamma ray flash. It was a little bit longer than normal. It had the usual spectrum. But the spacecraft was over Egypt. And there were no thunderstorms in Egypt at the time. However, there was a thunderstorm happening. Oh, didn't mean to do that. Let's get that back. There was thunderstorms happening much further south in Africa. There were other strange things about this event. This plot here shows time on the x-axis and gamma ray intensity on the y-axis. And what you're seeing is that there is one peak, but then if 20 milliseconds later, there was a second peak. And this is unusual. Terrestrial gamma ray flashes usually only have one outburst. Even more unusual, on this plot here, on the right-hand side, it's a spectrum. So you're seeing energy along the x-axis and intensity along the y-axis. And there's a large peak at 511 keV. This large peak at 511 keV is telling us that we're not actually seeing, likely to be not seeing gamma rays at all. What we're actually seeing is positrons, the antimatter to electrons, annihilating in the detector and producing that signal in the detector itself. And what we think is actually happening is that this region of the Earth is magnetically connected to this one. The Earth's magnetic field lines trace one to the other. So if we look at a model of what's happening, you have a thunderstorm. The pink are gamma rays. The gamma rays just spew everywhere when the particles in the thunderstorm are accelerated. But the particles themselves, they have to travel along magnetic field lines. So the particles don't spray everywhere. The particles follow the magnetic field line, and they stay bunched. So if we happen to be on that magnetic field line, the particles come straight through us, the positrons in that particle distribution annihilate in our detector, the particles go down, hit the conjugate point, and come back and hit us again. They were bouncing backwards and forwards, just as the particles do in things like the Van Allen belts. So we happen to be in just the right place to see both of these events, which is actually kind of extraordinary because you could be a plane and this would also happen. Okay, so moving on to 2010. In 2010, we found what's known as the Fermi bubbles. I mentioned these earlier. The Fermi bubbles are these large lobes of emission extending 25,000 light years above and 25,000 light years below are the galactic center. These lobes of gamma rays are telling us that that region in our galaxy contains higher energy particles. And what we think happened here is that a few million years ago, the black hole at the center of our galaxy was active and energized that region that then expanded out into intergalactic space. And these lobes are large. If you were to make an artist's rendition of where they would be relative to our galaxy, they're almost as high above our galaxy as the galaxy is wide. If you were to turn these lobes on their side, they would envelop the Earth. And it's amazing to me that we had no idea that these existed until we were able to see the sky with Fermi. When I did my thesis, we used an object known as the Crab Nebula as a reference source. And we were so sure that it was a constant, stable reference source that I didn't describe my objects in real units. I would say that this active galaxy had a flare of 2 crabs, because the crab was considered to be the reference source. We would check that our instruments work correctly by verifying that our measurement of the crab is the same as everybody else's measurement of the crab, because everybody knew that the crab was a bright, steady reference source in gamma-ray astrophysics. And then dramatically, we discovered that that is really not the case in high-energy gamma rays. So what you're seeing in the top left plot is gamma-ray flux as a function of time. And we had a huge outburst. And this huge outburst, at the time that this happened, it became the brightest gamma-ray source in the sky. I mean, it's not only is it not steady, it's dramatically not steady, it's insanely not steady. And the variability, the change in flux, was extremely rapid. And by looking at the spectrum, we could tell that this very, very rapid change in flux was happening with the most energetic particles in the source. And this completely changed our thinking on how you're producing extremely energetic particles in systems like the Crab Nebula. In 2012, we found the highest energy emission ever from a solar flare. This was the first time we were able to localize where on the sun the high-energy gamma rays were coming from. It was the longest gamma-ray flare that had ever been seen. And since then, we've actually been able to realize that we can see gamma-ray flares from regions that are behind the sun, and that the gamma rays themselves are actually being produced some distance away from the solar surface. In 2013, so all through the mission, one of the unique features in the gamma-ray range is that a leading candidate for the origin of dark matter, a weakly interacting massive particle, is predicted to produce gamma rays when it annihilates with itself. And this means that gamma rays are in a unique position to be able to directly see where dark matter is in our galaxy. And the places where you would expect to see this signal are the places where the dark matter density is highest. And the place where the matter density is highest is right at the center of our galaxy, right at the middle of the gravitational sink. And we had realized early on, but by the time we got to 2013, there was really consensus from many groups that we did have a signal at the center of our galaxy. And this signal at the center of our galaxy was not a point source, it was spatially distributed, which is what you expect from dark matter. It had a spectrum, a distribution of energies that is also consistent with what you would expect from dark matter. But the problem is that because there are so many other things towards the center of our galaxy, we couldn't yet draw the conclusion that we really were seeing dark matter, because it could also be consistent with a population of dim, unresolved objects, where each individual object is too dim to be seen by itself, but as an ensemble, it produces a glow. So in 2013, we spent a year with our observations focused on the galactic center to try and address this question. And I wish I could tell you that we had discovered dark matter. But we're largely concluded that it's more likely that this signal really is from a population of dim sources, which of course is interesting all by itself, but just not quite as interesting. In 2014, we had an amazing observation in 2009. we're looking at the sky all the time, and we find a bright new gamma-ray source. And this source is in the galactic plane. We want to know what it is, so we ask an X-ray telescope, or we go to ask an X-ray telescope, can you take observations of this new gamma-ray source that we found? And we found that the X-ray telescope was already looking there, which is ridiculous, because we haven't yet told them that we had a new source. And then we realized that the reason that the X-ray telescope was looking there is that an amateur optical astronomer in Japan had identified a new stellar nova. A stellar nova is when you have a kind of star known as a white dwarf that is accreting material from a companion. And when it accretes enough material, it has a thermonuclear explosion that produces a large outburst. It wasn't expected that these systems would produce observable gamma rays by Fermi. But over the years following that detection, we realized that in fact, gamma rays are a common form, commonly seen from novae. And now we've understood from the gamma rays that because gamma rays can only be produced by energetic particles, if we compare what we're seeing in gamma rays to what we're seeing in X-rays and optical, we can get insight into what's producing the emission across the entire range. And this is another example where the gamma rays have changed our understanding of how these systems work. Coming back to supermassive black holes. In 2015, we realized that we're seeing what looks like a potentially periodic signal from an active galaxy. An active galaxy is a supermassive black hole. You don't expect to see periodicity on timescales of years. One way that you could produce this is if the system is actually a binary supermassive black hole. In 2016, we completely revamped our data processing pipelines and significantly improved the quality of data from our instrument. We're now able to see the sky more sharply. We're able to see the sky more deeply. When we had completed the processing, it was the equivalent of adding overnight 1 whole year of observation power to the data set. And so what you're seeing are several before and after. So the bottom is what we see from the Crab Nebula before the change. The top is showing the improved pulsed signal from the Crab Nebula afterwards. This was a dramatic improvement. And this allowed us to do new things. And one of the things that we were able to do is we could take the supernova remnant, IC443. A supernova remnant is when a star reaches the end of its life and it explodes. It produces a shock that expands out into the interstellar medium. But the interstellar medium, the material between the stars, is not uniform. And in this particular case, the shock is expanding into open space in one direction, into a molecular cloud in the other direction. So you have quite different conditions in the different parts of the supernova remnant. And now, with the greater power that we had in our data, we were able to compare the properties of the gamma rays from the different regions in the supernova remnant. And when we did that, we found that, yes, the flux, overall intensity of the gamma rays changes, but the spectrum remained constant. And that was telling us that the spectrum of gamma rays that we're seeing is an intrinsic property of what's going on in the supernova remnant itself, and not something related to the external medium, which gives us confidence that supernova remnants are one of the places that are accelerating cosmic rays to extremely high energies, because these gamma rays are the signal of those cosmic rays. In 2017, we had, I think, one of the most exciting results of the mission. What you're seeing here on the bottom is a strain from a gravitational wave detector. What I'm showing here is LIGO Livingston. This event was also seen by another 2 interferometers, a second LIGO interferometer, and weekly by Virgo. And what happens is the gravitational wave intensity intensifies and goes to higher and higher frequencies until it goes chirp, and then it's gone. In this particular case, 2 seconds later, the Fermi Gamma-ray burst monitor saw a short gamma-ray burst. And this was the first time that we had seen photons and gravitational waves from the same object. What's actually happening here is you have two neutron stars that are rotating around each other. And as they rotate, they lose angular momentum by gravitational radiation and get closer and closer together until they merge. And at the point that they merge, they release a huge amount of energy that drives jets of particles out into the interstellar medium. In those jets, we're producing the gamma rays that we saw with Fermi. In the days and weeks following this, we also saw optical emission from this little region in here. And what that is the neutron-rich debris. Well, very neutron-rich, undergoes a sequence of nuclear reactions known as or-process nucleosynthesis, where you have so many neutrons that you can build heavy elements. So what you're seeing here is where we're producing the gold, uranium, the heavy elements. So this was just the best ever. Okay, so I've reached the end of my highlights. What time is it? Okay, good. Okay, so I've given you a snapshot of some of the results that I find interesting. But I could have given you another hour talk and talked about a completely different set of results that I also find extremely interesting. So what this chart shows is a quick summary of all of the science results for which we've issued a press release in the last 10 years. So we start close to Earth with terrestrial gamma-ray flashes of gamma rays from thunderstorms. We also see flashes of gamma rays from the sun. We see steady emission from the sun, from the cosmic rays interacting with the solar surface. We've seen pulsars, pulsar binaries, millisecond pulsars. I didn't tell you about how we were seeing pulsars in orbit around other objects and how those interactions change. We've seen novae, we've seen gamma-ray binaries, where we're seeing a star and a compact object in orbit around one another, showing periodic emission on timescales of years. We've seen supernova remnants and pulsar wind nebulae. These are the remnants of stars that have exploded hundreds or sometimes thousands of years ago. We've seen globular clusters, we've seen the Fermi bubbles, we've seen starburst galaxies, which are the equivalent of what we're seeing in the diffuse glow in our Milky Way, but in other nearby galaxies. We've seen radio galaxies, we've seen blazars, which are a kind of active galaxy. We've seen gamma-ray bursts. I didn't tell you that we can also use our instrument to detect particles directly. So we've made a measurement of the electron spectrum at Earth. We've done studies of dark matter. So my summary is very simple. The first 10 years of Fermi have been great, and I'm looking forward to what's coming next. We've done the things we expected to do. We expected to study pulsars. We expected to study active galaxies. We've done things we didn't expect to do. We did not expect to find the Fermi bubbles. We didn't expect to find novae. We definitely didn't expect, but we did hope, to be honest, that we would find a counterpart to a gravitational wave. And what I found so exciting about working on Fermi over the last 10 years is that each year has brought a really dramatic, impactful science result. And they just seem to keep on coming. So I don't know what we're going to see later this year or next year. But I'm confident that I'm going to continue to be surprised. Thank you.
You mentioned the measurement of the electron spectrum. You have capability of identification or separation between electrons and positrons?
We can separate electrons. So the electron spectrum that I showed there is electrons and positrons together. We can separate electrons and positrons indirectly using the Earth's magnetic field. Where one region is positron enhanced and the other is an electron enhanced. So from that, you can get a measure of the ratio.
You mentioned explicitly the flares on the 7th of March, 2012, which is exactly 7 years from today, no? The fact is that I'm working on those flares. It was NIX54 and NIX13, according to Gauss list. Well, you say that you identified gamma rays from these flares.
Yes.
Can you tell me, what happens with these gamma rays coming to the Earth? We know that the X-rays ionize almost everything in the ionosphere. What happens to these gamma rays, which are certainly of much, much higher energies?
So so you're asking what is the impact of the radiation for us on Earth? In this particular case, it's not intense enough to be that noticeable, and that's because while the individual gamma rays each one has a lot of energy, there aren't as many. There are solar events that can cause disturbances that we would notice, but the gamma ray, the solar flares that produce gamma rays often don't always have to be otherwise very intense. I'm not describing this very well.
Well, the intensity is low.
Yeah, so we can see, there are some cases, we don't see gamma rays from every solar flare, absolutely for sure. But interestingly, the solar flares that we do see gamma rays from aren't always the brightest ones. And the number of gamma rays that we're seeing from this solar flare at Earth, the rate of gamma rays per minute in the detector isn't very much higher than we're seeing from an active galaxy or from any other gamma-ray source. So while we can see it clearly, it's not very, very bright from the perspective of, relative to any other source. So the crab is producing as many gamma rays that are hitting Earth as the sun was at that time.
Thank you.
Thank you for a very interesting talk. I have a question. You mentioned these unknown sources that Fermi sees. So are there, I assume there are theories behind that, what these could be?
Yeah, so some people have hoped that some of the unknown sources might be produced by dark matter. If you imagine you've got a dwarf spheroidal galaxy, for example, that has very, very little normal matter, but a large amount of dark matter, then you could imagine having a gamma-ray source that would not have any obvious counterparts. The challenge is that the spectrum of that kind of source will look very similar to a pulsar, and we're now finding the most common counterpart to what we used to be unidentified sources is actually turning out to be pulsars. So just more examples of things that we already know about. It's just difficult to figure out from the gamma rays alone what you're looking at. I personally think that there are almost certainly new classes of astrophysical object in our sample that we're seeing the gamma rays, but we're not able to interpret them because we don't know what the underlying object does. So if you pick any kind of energetic object, it's possible to produce gamma rays from it, but it's very hard to prove that the gamma rays are coming from that kind of object without having things varying in step or very, very good spatial resolution or a period or something like that.
My interest is more on the instrument detection capability. So 10 years in orbit, I suppose the machines are done from earthly materials, which are subject to aging, perhaps degradation. How is this loss of detection performance perhaps accounted for in the analysis you do? I suppose that on day one, the detection capability or quality of measurements is not the same as 10 years down the road?
Actually,
or is
that's not entirely true. So the quick answer is that the scientific performance, I'm just going back to a detector slide so I can, but I've got to go a long way back. Let's go. The detector performance is essentially the same now as it was at launch. In fact, it's a little bit better because we improved our
That's
our
data
ground
processing.
analysis.
I'm speaking
But
about the...
the calorimeter, for example, as the cesium iodide crystals are irradiated, they become slightly cloudy. So the yield drops. And we're doing a continuous calibration, so it just becomes a calibration constant. So our ability to make an energy measurement hasn't been impacted, but we do need to constantly adjust a gain factor that we use in a ground analysis to compensate for that. In the tracker, it's a silicon strip tracker, and shortly after launch, a bunch of strips, a small percentage of strips, but a small percentage of 880,000 channels is still a lot of strips, died. But since then, we're getting noisy or lost strips at the rate of about 1 every 3 months. And losing 1 out of 880,000 every 3 months is not having an impact. There isn't really any other degradation that I can think of. We lost 1 readout on one side of 1 calorimeter log. There's no impact on the age-related impact on the ACD. So there really hasn't been.
So the follow-on question is, what limits the life of the Fermi satellite itself? So when does it become obsolete or useless to conduct scientific experiments?
We don't have any consumables, so in principle it should keep operating. Our orbit is, eventually you'll fall out of the sky, but that won't happen until after 2050. So I can't tell you what's going to limit us. Eventually something will break, and who knows what's going to break. We had a failure in one of our solar panels, so that's one. The solar panels rotate to follow the sun, and one is now fixed, which puts some constraints on where we can observe. But, I can't tell you what's going to make us end because, I'm hoping that everything just keeps on working for another 10 years.
Other questions?
This detector is detecting very high energetic photons. How many photons do you have to detect to be able to say that gamma ray came?
So we detect in total about 4 gamma rays per second. And at the same time, we're detecting about 4,000 charged particles per second. So one of the challenging analysis is to distinguish one from the other. We don't need very many gamma rays to identify that we have found a new source. So for example, if we are looking for a gamma ray burst where you have a very brief flash of gamma rays, 5 or 6 gamma rays can be enough to determine that we have found a new source. The brighter objects in the sky are going to be bright enough that we can detect them significantly every few hours. But for many of our objects, you have to wait for months or years to collect enough photons to make a significant detection. I'm not sure if this answers the question. But.
Basically, 1 gamma ray is 1 photon.
Say that again?
1 gamma ray, you said, is basically 1 photon?
Yes. Yeah, 1 gamma ray is 1 photon.
Okay.
Yeah, I'm sorry, I've used the terms interchangeably.
Okay, if there are not more questions, let's thank Julie for a very nice talk.